Look at the reaction time required here. Navigating a dynamic environment at highway speeds demands a decision in a fraction of a second. To make that single swerve, the vehicle's onboard sensors are generating gigabytes of dense telemetry every second. To be useful, that massive telemetry payload must be processed and converted into physical action within a low millisecond window. Historically, processing high-volume data meant sending it to centralized cloud topologies. This setup creates a core dependency. The vehicle acts as a collector, tethered via wireless networks to a distant server rack that runs the actual logic. But routing data through external networks introduces a bottleneck. Even with maximum bandwidth, round-trip transmission is strictly limited by geographical distance and the speed of light. To maintain real-time safety, engineers have to move away from the centralized cloud model. They are shifting the compute locus, migrating the logic directly to the silicon onboard the vehicle. Safe navigation is mathematically incompatible with the transmission delays inherent to centralized cloud architectures. To see why, we need to track the journey of a single telemetry packet in a cloud-tethered pipeline. The first delay is the uplink phase. The vehicle pushes dense data to a local cellular node. Then comes the transit backhaul phase, routing the data from the cell node across regional networks to reach the data center. This timeline charts the progression. Each geographical jump adds a latency penalty to our packet. At the data center, logic execution adds a minimal processing penalty. Finally, in the downlink phase, the command travels backward through the layers to reach the vehicle. The cumulative round-trip latency often breaches the low millisecond threshold required for safe driving. This delay is worse when streaming gigabytes of dense LiDAR point clouds. LiDAR uses pulsed lasers to build precise 3D maps. This massive data volume creates bandwidth congestion. Even with massive processing power in the cloud, the physical distance guarantees failure at autonomous speeds. To bypass network latency, engineers use an edge computing architecture. This requires physically severing the external network tether for all critical navigation logic. The solution is a localized micro data center installed directly within the vehicle chassis. Compare the paths. The edge native path has just 3 nodes: sensor, local silicon, and actuator. Miniaturized server hardware near the vehicle axle allows data to move instantly between sensor and silicon. Localizing the path entirely eliminates wireless transmission overhead. Without the transit delays, the decision loop operates within strict millisecond bounds. The trade-off is that localized hardware has less compute density than a server farm, requiring specialized silicon to handle the high volume. Moving the compute locus on board is a mandatory mathematical optimization for survival. The core challenge for this onboard silicon is ingestion, instantly absorbing gigabytes of unstructured, chaotic telemetry in real time. The edge hardware performs a localized triage. It filters critical navigation data, like obstacles, from non-essential sensor noise. This pipeline shows the process. Raw data enters, is compressed and filtered, and exits as a precise actuation command. That command triggers the steering or brakes immediately. It completes the loop without a single external network query. The Edge Microdata Center achieves high-throughput processing previously thought impossible outside of a centralized facility. Here is the Edge architecture operating in a complex city environment. This navigation is the result of a physical change in data handling. In the older model, the vehicle was a passive collector, waiting for external instructions to act. The new architecture allows for silicon sovereignty. In systems architecture, sovereignty means having zero reliance on external network availability or cloud uptime for critical operations. This guarantees survival regardless of network dead zones or cloud latency spikes. We identified cloud latency limits, shifted the compute locus, built microdata centers at the wheel. By bypassing cloud bottlenecks and migrating logic to the local silicon, the vehicle navigates as a self-contained unit, making its own decisions in real time.